So basically, I'm going to describe two prototypes for doing remixing and upmixing of musical audio using source separation. And so I'll first introduce a little bit the general technique, which you already heard. It's very similar to what Stelios just presented. And then I'm going to talk about each of the prototypes and hopefully demo one of them. So this work is done in the context of a project funded by EPSRC. It's a roughly three-year project. The project leader is Mark Plumley, and mostly on a daily basis is Emmett Grace, Andrew Simpson, and me. And we also have some people from Institute of Sound Recording at Surrey, Chris Hummerson and Rosanne Mason coming regularly. And basically the general trend in audio source separation, I think there's been a bit of a shift towards using more prior information. So in the past it was more typically thought as a blind source separation problem, where you could use the fact that if you have multiple microphones, then you can use some linear techniques to do blind separation, right? But now trying to tackle the more difficult problems of stereo and mono recordings with many instruments, people are using more and more supervised methods and prior information. And another change that is happening is that the evaluation campaigns, that is something that is done every year to compare algorithms, they also shifted towards using, instead of trying to tweak algorithms for a single song and kind of adapt to one song and do the best possible separation, try to have algorithms that can deal with 50 songs or train on 50 and predict on 50 songs. Sorry. So the general technique is usually based on time frequency masking, as you already saw. So that means we hope that the sounds won't overlap too much in time and frequency. And then we apply this kind of masks, binary masks. So when in the time frequency pins correspond to the wanted source, to the target sound, and zero otherwise. And soft masks are the generalized Billionaire filtering that Stylianos was talking about. So this should be an example of that, of a binary mask.
It was another lonely night, spent following the moon's guiding light, looking for something or someone to argue.
So, yeah, you couldn't hear it very well here, but the point was that this is the ideal mask, so we compute this one with having the original sources, and it already has some artifacts. And the problem is, so this was separating the vocals from mixture with guitar. The problem is if you make mistakes in this kind of mask, then the artifacts become very bad. So this is an example of a soft mask.
It was another lonely night, spent following the moon's guiding light, looking for something or someone to...
So you can hear that there's a bit more of the guitar in the background. It's still the ideal one, and it's already not perfect. But the thing is, if you make mistakes with this kind of mask, the result still sounds reasonable. So the technique that we're using, also I think most people are either doing deep neural networks or thinking about it. So this is more like a mainstream approach, I would say. It's a typical fully connected neural network with a few hidden layers. We play with 1 to 3 hidden layers as sigmoid activation functions. And we give it a spectral frame, sometimes with a context like the previous and the next frame. And we hope that it will learn to predict one of these masks. So the output is the ratio or the binary mask. So I'm going to show a little bit application of this to remixing audio. So the idea of remixing is to make one of the instruments louder or smoother than the rest. And here we're using this dataset from CSEC Challenge, which in order to do this idea of playing with many songs, they came up with this idea of general instrument categories that kind of work for popular music, like vocals, drums, bass, and other. Other normally is guitar or keyboards most of the time. Sorry, I'm going to need some water. So in this case, we use one neural network to learn to separate each instrument separately. And here, the technology, the implementation was also experimenting with web audio. So it means that basically all of it is implemented in JavaScript. So I'm not going to go into the detail. And as I said, it was one DNN for each instrument. And then we were using a binary mask because instead of using the mask to multiply the spectrogram, in this case, we're seeing it as a classification prediction. So for each time frequency bin, we're using the mask to tell us if that time frequency bin corresponds to some drum instrument or some bass or some vocals. And yeah, the training was done using this framework called Convert.js, which is quite cool. So we could keep everything in a web environment or using Node.js in this case. So, so this runs in real time. The training, of course, is done offline. And then the prediction is real time in a short time Fourier transform context. And then we do one prediction for each model. And then we take the predictions of each model as a kind of hint about what instrument this time frequency bin corresponds. But then instead of doing anything with it, we let the user modify the volume of each instrument and therefore scale the time frequency bin that we classified. And then we have like a general threshold slider that says, well, if the probability, we're treating it as probability, it's not really probability, it's the output of a sigmoid. But if it's below a certain threshold, we just ignore and don't deal with this time frequency bin. So let's see if I can get it to work. Oh, it's a bit of a problem with the resolution, but so this is a web demo, and I'm going to try to remix a little bit. So you can see I have sliders for drums. So I can make the drums low there, or the bass. For the vocals, it doesn't work so well in this song. Okay, so you get the idea. Back to the presentation. So then we tried to do similar thing for upmixing. So upmixing means take a stereo content, a mono or stereo content, and play it in a surround sound system. In this case, it was a 22.2 system. Using the same data set, so using the same instrument categories that I just described. And in this case, we found that this idea of using multiple models didn't really work. It produced many special artifacts, things that were moving very quickly around speakers. But instead, using a single model that would predict 4 soft masks from the final layer, this created very convincing results. I'm not going to be able to demo it. So I hope you believe me. In this case, the technological context was a neighbor project called S3A, Spatial Audio for the Home. It's a big EPSRC-funded project, collaboration between several universities and private entities. And they basically doing research in spatial audio. So they develop object-based specialization engine. So object-based means that in this case that we can give it tracks for different instruments and tell it where in space we want these instruments to be. So it's a bit of a black box for us. So I know it works, it uses a BBAP specialization. And it has like a basically a UDP interface. So we put an open sound control interface on top of it. And so we're able to play with it. And so in this case, as I said, there's one large neural network that that produces the 4 masks and soft masks. And in this case, training is using a stochastic gradient descent with early stopping and some features we added. And so here, the way it works is we do the extraction offline. So we get some estimates of the of the tracks corresponding to different instruments. And then in the listening session, we play this in sync. We plug them into the specialization engine. And then we use a mobile interface to tell it where in space will each instrument be. So the space, in this case, we mapped it into a kind of 2D plane in front of you. So here's a bit of a diagram, and the surprising fact is that it worked. So if you went very close to one speaker, you could notice that there was something going on. But if you sat more or less in the middle of the room or around the middle, you would perceive a good mixture of everything. And as long as the separation was good enough that you could move most of the energy of one instrument somewhere, the perception would be that the instrument comes from there, roughly. So it's not like our perception is not so picky in this case, and so this basically works. So I'm going to conclude. So the idea was that the current techniques that we have for source separation, they don't give perfect results for separation. It may be that they won't give perfect results for a long time. I will show you that in the ideal case, it may be better to use a soft mask, which already has some leakage from interference sources. So we can already use these tools in this space that goes from non-perfect to almost perfect for applications like remixing and upmixing. And here, basically, the difficulty, so that the way this performs depends on the difficulty of the mixture. So if the mixture has more instruments, if it's more complex, it's going to get more difficult. So what we need to do is to provide tools that can adapt to this somehow. So I'll really show you a little bit the mixing interface where, so basically if there was this control that originally we thought it worked because of the other category, which we didn't try to model, but it also works very well to adapting to the difficulty of the mixture. So that could work for like more experienced users, let's say, and for novice users, non-expert users like consumers. You could use interfaces that are more like limited. So, for example, in the upmixing interface, some people ask, "Can I listen to the original, to extracted sources?" And luckily they couldn't, because if you could, then the spell would be broken. But by not having this feature, you could play with something that seems to work. So that's the end of the talk, and thank you for listening.